All right, going to take a look at problem 6 from worksheet 2. We have these two balls, okay, and it says, hey, a blue rubber ball, okay, it's black, but pretend this is the blue ball, okay? B for blue, B for black, it works. Okay, you say, hey, it's moving east. It says, rolling along a smooth level surface, 15 meters per second due east. Okay. At the same time, headed due west is a red rubber ball, the same mass as blue, but moving at 22 meters per second the other way, heading west. It's like, oh no, right? It says there's going to be a collision. It says, hey, after the collision, boink, the blue ball is headed west at 21 meters per second now. How fast is the red ball moving? Okay. And then they're going to ask, is this collision elastic or inelastic? And have us explain how we know. So let's go to sketch. So you say, all right, I have a blue ball here, and that is heading east at 15 meters per second. Meanwhile, there's a red ball, and that red ball is headed west at 22 meters per second. Okay. Afterwards, they tell you the blue ball is going to be headed west at 21 meters per second. Okay. What's the deal with this red ball? All right. Okay. It was going faster. Maybe it hits it and keeps going. Maybe it hits it and bounces back. Not 100% sure, right? We'll have to do a calculation to find out. Okay? So that is it. That is the deal. So, you say, we're going to solve this with conservation of momentum. It's a collision. You figure your go-to tool for a collision is momentum. So you say, hey, what do you want to make your system? And you say, of course we want to do both the red and the blue ball. Okay, we're going to do red and blue. Okay, we're trying to find the speed of the red ball, but we don't know anything about the impulse that's acting between the force and the duration. We're going to need to combine them into one system. And so when I do my conservation momentum equation, right, I'm doing red and blue, so I can have change momentum of the red ball and change momentum of the blue ball. The outside force, horizontal force, they tell you we're going to assume it's a smooth level surface that we're going to have very little energy loss or rubbing or anything from there. So that's going to be zero impulse horizontally. So we're going to have the momentum of the red ball at the end minus the momentum of the red ball at the start, plus the momentum of the blue ball at the end minus the momentum of the blue ball at the start. Are any of these terms going to be zero? And you say, nope. Nope, nope, not sure. We're going to have to solve to find out. We'll put in there, assume it's there. So none of these terms drop, but I can go ahead and put in my MV terms now. This is going to be mass of the red, velocity of the red at the end, minus mass of the red, velocity of the red at the start, plus mass of the blue, velocity of the blue at the end, minus mass of the blue, velocity of the blue at the start. I guess I was supposed to color code these blue and red for you. It's all right. It's all right. Okay. Hey, do I know the mass of the red ball? Yes, I do. Okay. They tell me, wait, do I? You're like, no, son of a gun, they don't tell me the mass of the red ball. They don't tell me the mass of the blue ball. What am I supposed to do? Oh, wait a minute. They said they're the same. They said red rubber met ball of the same mass as the blue one. You say, no, wait a minute, this M is the same as this M, is the same as this M, is the same. Oh, all the terms have an M, I can just divide through by mass. How nice! How nice is that? Bang, 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 bang. All the M's go away because they're all the same. You say, oh, this is actually going to be really swift. Velocity of red at the end, that's the thing we are trying to find. Minus velocity of the red at the start. Let's make right positive, east positive. Let's make that then a negative 22. So that's a negative 22 that I'm subtracting, right? Okay. Plus velocity of the blue at the end, that's a negative 21. Okay. Minus velocity of the blue at the start, that's a positive 15. Okay. So that's what that looks like. So you say, This is going to be negative means positive, so it'll be 22 plus a negative 21. That's just 1. That's just 1 minus 15. That's negative 14. 0 is the final velocity of red minus 14. Look at the other side. 14 meters per second is the final velocity of that red ball. So it is going to be going in the positive direction. It's going to be going to the right. That's what it looks like at 14 meters per second. Ta-da! All right. So that's part A solved. Okay. But now they want to know, hey, this collision, was this collision elastic or inelastic? Right? And so you say to yourself, well, how do you know if a collision is elastic or inelastic? What's the difference between those collision types anyway? You remember that in all these collisions, momentum is conserved, but kinetic energy may not be. Some of that kinetic energy might go into other forms, like thermal energy and vibration and stuff. And so you say, okay, I just need to calculate the kinetic energies before the collision and the kinetic energies after the collision and see how they compare. If the collision is elastic, that means the total kinetic energy stays the same. All right, kinetic energy is conserved. So that's what we're going to do. We're going to check then. We're going to say, hey, the kinetic energy at the start, is that the same as the kinetic energy at the end? That's what we'll check. So kinetic energy to start, that'll be the kinetic energy of A and the kinetic energy of the blue ball and the kinetic energy of the red ball. So that'll be 1/2 mass of the blue ball, velocity of the blue ball at the start squared, plus the kinetic energy of the red ball, 1/2 mass of the red ball, velocity of the red ball at the start squared. Is that equal to the kinetic energy at the end? 1/2 mass of the blue ball, velocity of the blue ball at the end squared, plus the kinetic energy of the red ball at the end, 1/2 mass of the red ball, velocity of the red ball at the end squared. Okay, are you okay with what I did here? I think that's okay, right? Makes sense? Starting energy and ending energy are the same. Okay, hey, again, you go through to plug values in and you realize, hey, what's in every term? Well, there's a 1/2 in every term. I can multiply by 2 and then go, oh, okay, multiply by 2, bang, 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 all those halves go away. The masses are the same with the two balls, and there's an m in every term. I can just divide by the mass, bang, 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 all the m's go away. I just have velocity of the blue ball at the start squared plus velocity of the red ball at the start squared equals velocity of the blue ball at the end squared plus velocity of the red ball at the end squared. And say, I know all these values, okay? Blue ball at the start, 15 squared. Velocity of the red ball at the start, 22 squared. Is this, in fact, the same as, on the other side, velocity of the blue ball squared, 21 squared, right? Okay, again, does it matter if it's positive or negative direction, by the way, on these? No, they're going to be squared, right? The sign's going to drop out. And velocity of the red ball, and its kinetic energy is just speed anyway. We don't care about the sign on these speeds in this. And velocity of the red ball at the end, 14 squared. There we go. So is this equal to this? And you say, look, 15 is bigger than 14, 22 is bigger than 21. This side is going to be bigger than this side. This is the starting kinetic energy. This is the ending kinetic energy. Oh, yeah. The ending kinetic energy is less than the starting. That makes sense. We have all this kinetic energy, and then some of it goes into vibration and stuff afterwards. At the end, the kinetic energy is less. This collision is inelastic. Okay, inelastic. Okay, some of these do not equal each other, as it turns out. So this collision is inelastic. Is this the special case that we call perfectly inelastic? No. Perfectly inelastic is when they move together afterwards as one unit. These have different velocities at the end. This is not perfectly inelastic, it's just inelastic. Kinetic energy not conserved. All right? And that is problem 6 from 6.